Hello, everyone. Thank you for coming to our talk. My name is Srdja, and for the past 2 years, we have been developing this game called Spellsouls. We wanted to bring console-quality graphics to mobile, and we faced a lot of challenges, a lot of difficulties, but it was also a very fun and rewarding experience to actually do cool stuff like this on mobile devices. And we want to talk about what we did, why we did it, and how we did it. So hopefully you can use that to make your games look even better. But let's start with introductions. This is my colleague, Joseph.
Yeah. Hi, everyone. I'm Joseph. So we are guys from Nordeus. We were mostly working on graphical stuff, technical stuff. So whenever something's not working, it's our job to fix it. So as my colleague said, so we are going to talk about this technical stuff today. So it's not going to be a post-mortem on if something's not working, do it better or fix it. It's going to be an actual concrete stuff on how you can fix some stuff that's not working. So first of all, let's talk about our company. So we're from Nordeus. Nordeus is a company based in Serbia, in Belgrade. We have 2 live games. One of them is Top 11, our massively successful game, which has more than 160 million downloads and is played all around the world. The other title is Spellsouls, what we're going to talk about today. It's currently in soft launch in multiple countries, well, we'll see when it's going to be full launch, actually. Let's talk about Spellsouls, since this is the topic of interest. So first of all, we wanted to bring AAA console graphics to mobile. You can imagine like a big AAA title and being played on a small screen. So this was our first of our visions. The next thing is we want it to be available to be played by as many users as we can find. So a wide range of devices. This means our lowest end device currently is an iPhone 4S. So you can imagine if a AAA title can be played on an iPhone 4S, at least the experience to feel like it's a AAA quality. Because when we say AAA, we don't mean a huge budget in tens of or hundreds of millions of dollars. We mean the feel of the game, to have a premium feel, a feel of quality. So to demonstrate what we're talking about, I'm just going to play a quick video that kind of gives the feel of the game, how it looks like. So here it goes.
Victory will be mine.
The fight must begin.
So, yeah, thank you. We are very proud of this game because we think we did succeed with our goals. So the game is a card collecting game. It's a real-time PvP battle arena game where 2 wizards are fighting with a bunch of minions and a bunch of spells flying all around the place. So, well, you can imagine the technical challenges that we might have had with bringing this to mobile. So, first thing, these are the challenges that we had, and we are going to cover them in this talk. We had many more challenges, but of course there is no time to talk all about them. But you can, of course, catch us after the talk and talk about everything that you want to hear. So, first thing is our PBR shading. PBR shading is challenging even on the PC. Okay, nowadays it's a bit more common. But on mobile, it's a nuance, mostly. So since we wanted to have a dark art fantasy world, realistic dark art fantasy world, sorry, this was the logical step to take. So take some PBR shader that can solve this issue for us. The next thing is everybody who worked with Unity, with a lot of graphical stuff in Unity, he probably encountered a problem with a lot of shader variants. So we had to solve this problem as well. Next, our goal was 60 FPS. Well, in the beginning, managers thought like it would be okay to go with 30 FPS, but when we showed that we could go to 60, it was like actually a massive success because everybody saw like this is what we want our users to have in our game. So how to optimize to silky-smooth 60 FPS? And the next thing is, of course, a iPhone 4S has drastically worse hardware than a iPhone 7. So a toaster, basically, compared to a normal computer. And we have some graphical scaling, so we're going to talk about them a bit today as well. So first of all, talking about PBR Shader, Srdja is going to take over this part. So Srdja.
Thank you. So yeah, PBR shading on mobile. Usually when you think PBR shading on mobile, you think, oh, I'm only going to be able to run this game on iPhone 7, maybe iPhone 4S, and it's not going to work, it's going to drop frames. But that's kind of both true and not true. There are two sides to that. So it is not possible to bring PC quality PBR shading to lower-end devices, because they're simply going to melt. But you can actually bring something that looks extremely similar and also follows a lot of PBR principles to mobile. The reason why PC PBR shading is very expensive is because of its lighting model mostly. It's using GGX, which looks extremely nice, but GGX is extremely expensive and it cannot run on anything except the most high-end devices. So the first thing we did is some research into that area, and we decided to go with the normalized bling foam lighting model. We did that in collaboration with artists. We did a lot of research in different ones, and this one had pretty much the best performance, and the quality was also there for us. Because phone screens are really small, so you can do a lot of approximations, you can do a lot of tricks to make it seem like full PBR, but it actually isn't. And another thing that you might have already heard if you went to our colleague Johnny's talk about VFX in this game. Say hi, Johnny. And the thing is that our artists are awesome, as I'm sure yours are as well. And we want to give them all of the tools that they need to create what they want. So we want them to have as much control as they need to bring their creativity into the game. So one of our core concepts for creating shaders is like freedom for artists, like a very, very general idea. But the concrete implementation is that when we are creating shaders, we expose all of the features that artists could possibly use so they can actually tweak them. And we did a couple of special things with our shader. If we were talking about PBR shader in general, we could stay here for 3 hours, so we're just going to mention the specific tricks that we used. The first thing when you have a PBR shader is that you can do cool stuff like this. You can have a character that has a bunch of different materials on him. So he has some grayish skin, he has some cloth, some metal, and some rocks, magma and lava and stuff like that. And you can do this by using a PBR control map. It's a basic of PBR. So everything on this character is one Unity material, but he has a bunch of physical materials. And usually how you would do this, you would put roughness and metalness into your control map. And that's how we started. But when we were developing the game, we found out that this was not enough for us. So there are two reasons. The first one is that there are some expensive calculations that you need to do using roughness and metalness. And the second one is that our game is still a fantasy game. So sometimes, like in 98% of the time, our artists want to do full PBR, everything realistic. But there's that 2% of the time where you want something to be really eye-catching, to look really weird and really specific. And they wanted to break PBR sometimes, which we think is cool, because we're not doing a full realistic game. So for that reason, we actually added one more thing to our PBR control map, reflectivity. So calculating reflectivity in the PBR shader is kind of expensive. So you can actually change that by using a PBR control map with 3 maps in it. One of them is reflectivity. So it allows our artists to break PBR when they need to, and it makes the shader cheaper to calculate. So how are the maps used? Roughness is used in a completely standard way. Reflectivity simply describes how much the environment Q map is reflected on that part of the character, and metalness describes if the reflection is colored by the albedo. So we have our character now, but the second staple of PBR is that it should look good in any environment, and to do that, the character needs to receive ambient light. And the best way to do that on mobiles is to use glossy environment Q maps, natively supported by Unity. You simply bake the environment into them and use them for reflections. They go all the way from completely mirror specular reflections down to completely diffuse reflections depending on the roughness. And Since this is a PBR graphic stock, we had to put this sphere somewhere is a rule. So yeah. And this is all pretty basic, but the special thing that we did, we want our environment queue maps to be able to light the objects. We want them to be able to light the objects very intensely, so we need some pixels to go over 1. But to do that on mobile, we would need to use HDR textures, which is not possible on all devices. The support is very spotty. So we did something that we internally call HDR emulation. And what we do, we increase the dynamic range of the queue maps inside of the shader, so the bright parts become even brighter and they go over 1, and the dark parts become darker. And you can actually see how the second queue maps look so much more vibrant. Even the one that's completely rough looks kind of blue, while the one up there looks gray. This really gave liveliness to our characters that are reflecting a lot of light. Next, we have a character. It has ambient light. We need some shadows. So the character over here has dynamic shadows, and the ground has light maps. So we use a combination of both for our game. I want to talk about dynamic shadows first. Whenever we're developing a feature, we actually think, does Unity support it? And in the case of shadows, it does. But do we actually need all of Unity's functionalities? From the trailer, you could see that our game is very, very top-down. And Unity shadows have a lot of features, and they're awesome for first and third-person games with all of the cascades and stuff like that. But for a game such as this, we don't need all of that functionality. So we decided to try our own shadows, and we implemented a completely basic system of dynamic shadows, which have one shadow camera pointing down, using PCF, percentage cover filtering. They sample the shadow map multiple times to make the shadow edges slightly smoother. And these shadows are actually faster than Unity's, and we have more control over them. So whenever you're doing stuff like this, you should ask yourself, can I make it slightly better for my use case? And do I have time to do that? In our case, we had the answer of yes to both, so we did it. And the trick here that we're using, you might notice it if you see that shadow moving down into the light map. They actually blend perfectly together. So if you do a completely basic implementation, those two shadows will overlap. And that looks really weird if you're doing a realistic game, because our brain is noticing those shadows all of the time, and in the real world, they are not placed right on top of each other. And you get some subconscious weirdness over there. So we made it so they completely blend nicely together. And how we did it. So our light map is using RGB channels for lighting, because we also want to bake lights into it. But calculating how much something is in the shadow when you have a full-colored light map is very hard in the shader, very computationally expensive. So what we actually did, we baked a static shadow map. That's a grayscale texture. We placed it into the alpha channel of the light map, and we simply use it to combine these two shadows very cheaply in the shader. You might be wondering, how can I do that with Unity's light mapper? And the answer is you cannot. So we're actually using V-Ray for all of our light maps. It's both a tech and an artist decision. From tech side, it allows us to do cool stuff like that. And from artist side, they have full control over how they're baking light maps, what objects will cast shadows on what objects, which objects will receive which lights. And the final bake is actually higher quality than the current light mapper in Unity. Yeah. OK, everything is now shadowed. It's time for dynamic lighting. So we want everything to be vibrant, to be moving. So we have a pretty standard one direction light, totally standard. But the focus of our game are spells. And we want spells to look as best as possible. We want them to be complete eye catchers. So we also wanted them to affect the environment. For that reason, we actually implemented 4-point lights. And those point lights are only used by the spells. We're actually using forward rendering in our game, because deferred is still too expensive. And if you do forward rendering on mobiles in the standard Unity way, you're going to render the object. Then on top of that, you're going to render one light additively, then the second, and the third, and the fourth, which ends up with 5 draw calls, which is very CPU expensive. So what you actually want to do when you're writing your shader, you want to make it so it accepts all 4-point lights at once and renders them all together. That's going to end up with 1 draw call only. But there's a problem. So it will be more GPU expensive. So what we did, we actually created multiple variants of the shader. We have a variant with 4 lights, with 2 lights, with 1 light, and with 0 lights. And depending on the number of the lights in the scene, we change those shaders. So when there are no spells and there are no dynamic lights on the scene, we're using the cheapest possible shader to make sure the device works as well as it could. And for that 1 second, when there are 4-point lights, we're using the most expensive one. Yeah. So since we, OK, yeah. Draw call state. So we started developing in Unity 3. And the thing is, back in Unity 3, when we wanted to have a transparent object and an opaque object, we had to write 2 shaders. One, yeah, I can see some head nods in the audience. So in some version of Unity 5, we're not sure which, they actually added the option where you don't have to do that anymore, but I never saw it in any release notes. So you can actually change these properties on the material like this. And that's what we showed for our VFX shader. All of our shaders have settings like this. And we put a link here. In case you can't read it, you can download it from there. Yeah, I'm going to wait a little bit for you to write it if you want. It's also going to be on the last slide, so don't worry. Yeah. So before we had like 32 variants of every shader for all of these combinations. Yeah. So that's mostly what we do for PBR. This is our quick tip to you, because this is 1 sentence in the documentation in some random place. And the next thing that we want to talk about, we have our own shader. It's written. It's actually running. It looks pretty nice. The performance is good. But we had some problems on the device when we were trying to load stuff. And Joseph is going to tell you what happened.
OK, so we have our big shader. So when I say big, after doing all these things, this is kind of how our, this is only the inspector part of the shader. So there's a lot of variables that can be changed. These are all adjustable by artists. So as we said, we want to give the artist as much control as we want. The problem is not if you have 1 of these shaders. We have 2, like 2 huge shaders with a lot of variance. And if you're familiar with Unity keyword limitations, you are going to hit them really fast doing this. So we hit the Unity's 128 keyword limit back in the day really fast. It is increased now to 256, but we still feel it's a temporary solution, and we would sooner or later hit this limitation again. So we had our problems. First is the huge number of variants, which is mostly, well, it's mostly because of these keyword limitations. And the next thing is that loading our game, loading the battle part, so we have the UI part and the battle part, took over a minute. This is no good because the user won't wait for a minute to play a 3-minute game. It's kind of unacceptable. So what could we do? Well, first thing, let's analyze the problem. So let's see what we can do better. Better than Unity's built-in solution. First thing is that we notice that certain multi-compile combinations are unnecessary. So as we talked, we have a shader that accepts like 0 lights, 1 lights, 2 lights, or 4 lights. So these are all multi-compiles, and these are different variations of the shader. But we also have another setting that defines if the shader is going to receive fragment lights, vertex lights, or no lights at all. So you can see if you define in the shader, in a material, that you don't want to have lights on these shaders, you don't need the variations for different light counts. So this would kind of save at least 4 variants on a single shader if the artists are not willing to use lighting, dynamic lighting on this shader. So this is the first thing that we saw we can optimize. The next thing is, OK, we needed something in between a multi-compiler and a shader feature. I'm guessing you're familiar with what multi-compiles and shader features are, but I'm just going to explain it for the sake of, I don't know what. So multi-compiles, basically, if you say that a shader has 2 multi-compile keywords, it will always generate both of the variants. If you say a shader feature and you set 1 keyword, then it will generate only that variant if it's actually used in the project. So it's not generated by default, it's just generated by need. The other always generates. And we needed something in between. So as we said, again, coming back to, we want to give artists as much control as possible. So we made them not everything has to have, for example, a normal map. And if an object has a normal map, then it's OK when we are scaling down our shader, because we want to turn off normal maps on very toaster devices. It's OK to generate a variant where you have a normal map. So a multi-compile is OK. But if an artist doesn't want a normal map on an object, then you don't need the variant of the shader when you have a normal map. So this cannot be really solved in Unity's implementation, and you need something in between a multi-compile and the shader feature. So the conclusion is, of course, I mean, we stopped using Unity's variant system, and we decided to implement our own. Our own variant system is very simple, although it sounds intimidating and complicated. It's based on two parts. So first part is a master shader. So this is the shader that is, well, 99% similar to the Unity's shader. So it also has some multi-compiles and shader features. But the thing is that we're not using this shader anywhere in the project, and it's forbidden to be used. And every time an artist clicks an option, so a checkbox like make a normal map for this material, make a variant with a normal map, then we generate a variant of this shader. This is a completely separate shader file that exists in our project. And as you can see in this picture, I hope you can see, so what we do is we just replace the multi-compile line with a /define, a hashtag define, in that line. So all we do is we just replace all these defines, and later these defines are processed by the compiler in our Srdja-include file. So it's kind of simple to do, but sounds very intimidating. In the end, we end up with a folder with a gigantic number of shaders, but it's still, by our estimation, around 3 or 4 times less variance than the Unity system. So it increases our loading times. One small thing that we wanted to mention here is we had a problem that when you make a shader, you edit a shader, you need to wait a minute to import it. And when you want to make a very small adjustment to the shader, this is, again, unacceptable. I mean, your workflow just becomes very, mostly like looking at progress bars. And that's not what you want to see. So what we realized is we were including the Unity Srdja include file. And since this is a huge file, it really needed time to compile. And not only that, but it also includes other files in the Unity system. So just removing this Srdja-include file, we increased our compile time by 10-folds, maybe 100-folds. So instead of looking at progress bar, it was almost instant. And what we did is we copied the part of the Srdja-include file that we actually used. So this helped us with the workflow, and only thing that we remained including from the Unity system is the HLSL support, because it does not actually include other Unity files. So it's safe to include, and it's not that long. So this will help you with compile time of the shader. So yeah, we talked about now the PBR shader, talked about how to handle variance problem. Next thing we want to talk about is a bit of optimization. So what we did to optimize both the CPU and the GPU. So yeah, Srdja, take over again.
Yep. So when we're developing games and optimizing them, we need to target something. Obviously, we target frame rate. And what I'm going to say next might seem really obvious, but when you're in that crunch mode, you need to ship your game next week, and it's running at 10 frames per second. It's very easy to forget these things, because mobile devices are portable, they have batteries, and they also don't have any active cooling. So you need to be very careful, because even if you make the best game possible that runs at 60 frames per second, but it drains the user's battery in like 15 minutes and also causes burns on his hand, what did you really do? So whenever we're optimizing, we are always considering all of these three things at once. And I also want to say a short disclaimer about 60 FPS in our game. We don't try to force 60 FPS if the device will overheat if it's doing 60. So what we actually do, we go 60 for high-end and mid-end iPhones and high-end Androids. Everything else is usually kept to 30, mostly because of heating. And before we actually get to all of the optimizations that we did and that you could also use, we just wanted to talk about a little bit about graphics profiling. I know you should do it, but we actually wanted to go with a story, what happened to us like 3 years ago. So 3 years ago, when we were developing a shader for another game, we were developing it. It looked really cool in the editor, and it was time to test it on the device. So we started building, and our game was pretty large even at that point, so there was a progress bar. It took like 15 minutes. And I was staring at that progress bar for 15 minutes just to see how it looks on the mobile. And it went to a mobile, and everything was pink. So, OK, we don't know what's wrong. There are no error messages anywhere. Let's try to modify the shader a little bit, remove some parts, see which one is causing the pinkness. So let's do that again, build again, another 15 minutes. And that repeated for about 5 or 6 times. This can also happen when you're optimizing because you're not sure which parts cause what problems. And back then, we were very tired of that because myself personally, I want to create cool graphics. I don't want to watch progress bars the entire day. And that's when we discovered our probably favorite profiling software, not because of its profiling features, but because it actually allows you to change shaders directly on the device without recompiling. And it takes 1 second to do this. This is a screenshot from Adreno Profiler, actually. You can, when you capture a frame, you can see all of the shaders, and you can edit them. If you ever use the Adreno Profiler, you know that the shaders are slightly obfuscated, so they're kind of harder to change. But the cool thing is that you can actually open the Unity editor. You can tell it to compile the shader, and you can paste that code into Adreno Profiler, and in 1 second, it will be on the device. That's one thing that I love about the Adreno Profiler. And the second thing is that it tells you exactly how many shader instructions your shader has. It even separates them into categories. So the shader performance cost is usually approximated by the amount of screen space it takes times the number of shader instructions. So you can pretty easily estimate how expensive your shader will be looking at this. Yeah. We're going to get back to shader instructions shortly. But before that, we just want to mention how we actually measure stuff. And because there are some traps that you can easily fall into if you don't know about them. So the first one, I'm just going to read directly off the slide. Yeah, you should never measure FPS in development mode, ever. So this sounds very counterintuitive because development mode was made for profiling and measuring, and it's awesome for finding bottlenecks in your code, but it adds a lot of overhead, and what's worse, it adds different amounts of overhead to different parts of the code. So what you see in development mode is not what your user will see. The worst case scenario, you should just create an FPS counter and put it on the top left of your game and test it in non-development mode. That's the first thing. The second thing is related to this graph. This is approximately 30 minutes of gameplay, and it's running our performance test. Our performance test takes about 1 minute, and it's repeating constantly. But you can notice that the frame rate is not the same during the entire test. So during the first 5 minutes, it's 44 FPS. After that, it's 25, and 15 minutes later, it's 16. And if your user gets a game with 16 FPS, I'm not sure he will play it. Personally, I wouldn't. And this actually happens because mobile devices now are extremely powerful. Their CPUs and GPUs are extremely powerful, but they have no active cooling. So they can literally cook themselves to death if they become too hot. So when their temperature rises above a certain point, they throttle, they reduce their frequency. That's the first drop. And when that happens even more, the second drop happens. So what we do for testing, we actually warm up our device before we test, because we want our users to play the game more than 5 minutes, and that's when the first drop happens. So we warm it up until the first drop happens, and then we actually start measuring performance. And you might be wondering, is there a way to avoid this? Well, there is a way to mitigate this by a huge amount. And that's what we do for all of our games. When we measure performance, we first warm up the device. And the first frame drop happens. Then we decide what we want to target with that device. For example, for this device, we would probably target 30 FPS because it cannot reach 60. And what we actually do, we make it run at around 40 FPS. And after that, we cap it to 30. That way, you're sure that you're not using all of the available resources on the device, so it will not heat up as much, and this drop will happen much later. So you should optimize for higher FPS than target. Just for reference, we actually optimize for 80 FPS if we want to cap the device to 60. that's a little bit about measuring, and now on to performance optimizations. The first thing that we always do when we're writing shaders, we optimize shader instructions. We try to reduce them as much as possible. This is a pretty obvious optimization. But what's so not obvious is that you should watch out for no-ops. These are kind of shader instructions that Adreno Profiler reports, but what they actually mean is that your GPU has stalled while executing your shader. That can happen for many reasons. Maybe you have texture fetches that are trying to fetch from UV coordinates that are not yet calculated. In the documentation, those are called dependent texture fetches. Maybe you have if-else branching. Maybe you have for loops that have a variable number of iterations. Maybe you're converting between half and float types. That can also cause no-ops. And maybe you have them for some very weird reason. And I'm just going to show you what happened to us about 6 months ago. So we were researching GPU matrix skinning, GPU skinning techniques. And if you ever did those, you'll notice that this is the most basic matrix palette skinning. It's also used by Unity to do GPU skinning. And we were comparing performance of a lot of them. And when we benchmarked them, this one was performing way below expectation. So we took Adreno Profiler and started poking around in the vertex shader. And we discovered that this line and a couple of lines above it and below it actually have 250 no-ops, which is kind of ridiculous because our entire fragment shader has 250 instructions. So we tried moving stuff around, checking what happens without actually changing the functionality of the shader. And we actually ended up with this. So the code is functionally identical. It will calculate the same exact thing. The only difference is that the array fetches are a little bit above the calculation. And when we did that, Adreno Profiler suddenly reported that there are 180 no-ops. This is kind of abstract, and we weren't sure what would happen, so we reran the benchmark. And we figured out that this shader was 20% faster for like 30 minutes of playing around with it. So it was a pretty big gain for us. And stuff like this can actually happen. So whenever we write a shader, we actually go through it in Adreno Profiler to see if there's any weird things, because shaders go through multiple compilation cycles, from CG to HLSL all the way to GLSL. So weird things can happen. So we also suggest that when you write a shader, you also check it in Adreno Profiler, change some stuff around, and see if you can get some easy wins like this one. Yeah. And finally, this last thing is also kind of obvious. You should always use half instead of full precision, because mobiles calculate half much faster than full precision. They calculate halves much faster than floats. But what's not so obvious is that desktop GPUs don't actually support halves. So everything is calculated in full precision. So you might end up with stuff that looks good in the editor, but when you run it on the device, you get some color banding or some very weird issues. How we actually do our shaders, we write everything as half, then we deploy to device with multiple test cases, and check if we have any banding issues. If we do, in Adreno Profiler, we start changing precision until we get all of the issues resolved. And one more thing, this is kind of obvious, but the not obvious thing is that you shouldn't use fixed precision. Because most GPUs on mobile don't actually support fixed. They're going to use half instead. And even if they do support it, conversion between fixed and half is not that cheap, and you're going to need to convert a lot. So that's a little bit about optimizing shaders. And now we just want to mention the probably biggest GPU optimization that you can do, and probably also the easiest one. And it's called upscaling. And it's completely based on the fact that modern phones have crazy resolutions. My latest phone has a 5-inch screen and 1440p resolution, and I can barely notice a difference between that and 1080p on the same screen size. If you're doing VR, you will notice a difference, but if you're not doing VR, it's simply not noticeable. But the thing is that 1440p actually has 77% more pixels, so the GPU is doing a lot more work, especially since mobile GPUs are mostly fill rate limited. So what you actually want to do, you want to render your scene in low resolution 1080p, and then let GPU hardware upscale it to full resolution. You will gain a lot of performance that way. And we do that for almost all devices. But there's a problem. So maybe you have a really, really bad Android device, and it has a 1440p screen. It happens. But you need to upscale from some real low resolution like 720p. And your UI is very sharp, and it needs to be very readable. But if you upscale everything, it will look blurry. The good news is that there are two ways of upscaling. One is hardware, where you let the hardware upscale everything. That's what we actually use because our UI in the game is not, our UI in the battle is not that detailed. But you can also use software upscaling. That means that you create a render texture on your own that's low resolution, render everything 3D into it, then by yourself you upscale it to a high resolution render texture, and on top of that high resolution render texture, you render your UI. That way you have full resolution UI, low resolution 3D scene, and everything looks okay. One problem that upscaling does have, when you're upscaling from a really low resolution, RJAG is due to aliasing. But the good news is that phone hardware is actually created to solve that issue by itself. Because multi-sample anti-aliasing on mobile phones is actually free now, or mostly free. There's actually an asterisk there because we're sure there's some situation where it's not free, but in none of our performance tests we've been able to find a situation in our game where it actually costs any performance. And finally, because phones are fill rate limited, the biggest, absolutely biggest performance killer for phones, especially a little bit older ones, is Overdraw. When you're simply rendering a bunch of transparent objects right on top of each other, you're going to end up with a lot of fragments that you need to combine to get your final pixel. And we are really careful about overdraw because on older iOS devices, it completely kills performance if you overdraw just half the screen. But the thing is that overdraw is kind of hard to measure. And a lot of the times, I actually get a call from an artist to come by their computer to check something out. And they show me a overdraw view, which looks something like this. And they ask me, is this too much overdraw? And I don't know. I simply don't know, because this is a pretty black box thing. It has some colors in there, and human eyes are not very good at judging precisely what colors are. So you can, if this picture was completely white, it would obviously be too much overdraw. But with this, we're not sure. And we try to solve that problem. And the good news is that you can actually measure overdraw completely precisely, as in get a number with 3 decimal places that describes how much of the screen you're overdrawing. And you can do that using a compute shader. So me telling you this doesn't mean much, so we also put that compute shader and the tool for measuring overdraw on this link. So we're hoping it will help you. It helps us a lot. We actually do automated testing for our spells by having artists just press a button, the spell casts, and this actually measures how much overdraw the spell has. And we have some limits depending on what rarity the spell should be. Epic spells obviously can withstand more overdraw than common ones. Yeah. And if you're targeting 60 FPS, we just talked about GPU optimizations now. You obviously need to optimize your CPU a lot as well, because 60 milliseconds is really not a long time if you have a lot of game logic and a lot of graphical stuff to draw. And Joseph will say a few words about some techniques that we use.
Yeah, okay, thank you. So there are of course, a lot of CPU optimizations out there, and we use a bunch of them in our game. But we're just going to talk about actually 2 things that we did that maybe are easy to forget and are left kind of the last thing in the project. First thing that I wanted to say is that loading and instantiating is expensive. I think everybody knows this, but let's just remind ourselves. So instantiating game objects is expensive. So not only that, but loading textures, loading shaders, everything is quite expensive. And it's no good if you have a 60 FPS game that kind of drops from time to time, because it's not a smooth experience, and it's noticeable. It's usually, I think it's better to have a 30 FPS game that doesn't drop than a 60 that drops every 5 seconds. So you really should, so yeah, this is how it would look like on an FPS graph. So you kind of have a smooth experience, and then it drops, and then drops again, and something additionally instantiates, and so on. So what you really should do is, we cannot stress this enough, is reuse objects. So you should really, whenever you create an object, just leave it in a pool and deactivate it after you're done with it. Deactivate it, hide it, do whatever you like with it, whatever suits your needs. And then when the same object, same prefab is needed again, just show it again to the user. So this will avoid this instantiating time, and you will end up with a smoother FPS. But one interesting thing that we should mention here is warm up your shaders. The best way that we found doing this is that it's not enough just to load a shader or load an object that uses a shader. You should actually render it once. So what we do in our loading screen is that we take all the materials that we need in the scene, and all the variants actually that we need in the scene, not only the material, all the variants of the shader that we need in the scene, and we put it on a quad that's never visible, and we render a frame with it. And this removes, this actually completely loads the shader, compiles it and loads it, and no additional work will be needed when they're required again. So after doing these two things, we end up with a FPS that looks completely smooth. Well, you have these small like jaggies, but that's actually not noticeable. So it's mostly it's a measurement problem. So it's smooth. Yeah. So the next thing that I wanted to say is view interpolation. So it depends on the nature of your game, but it's a good practice usually to separate your game logic from your view logic. So the important thing that when you do this separation, you don't have to run the game logic and the view logic at the same time. So what we do is we do this. We run our game logic at lower FPS. If we try to run the game logic at 60 FPS instead of 20, what we are doing, we save like third of the 200% faster. Let's say it like that. So it's 200% faster to do it like this. So what we do is we run our game logic at 20 FPS instead of 60 FPS. I know some other guys run it even lower, maybe 5, or I even heard about 4 FPS. We didn't want to go that deep because we found that 20 FPS for us is quite enough, and we get enough performance out of it. And so view interpolation, just mention how it works. You basically use it on position mostly. What you do is you save your previous position of a view and interpolate linearly between the current position and the previous position, depending on the time how much it takes to reach the next game logic tick. So it's simple to do. If you organize your code, it's a piece of cake. If don't, I always recommend to reorganize your code. Okay, so these are some CPU optimizations that are kind of interesting. The next thing that we should talk about is graphics quality scaling. So as I said, a toaster doesn't have the same performance as the iPhone 7. So it's obvious that we cannot run the same thing on both devices. What we did is we exposed everything that we thought that might be a bit expensive to be a quality setting. So these are just some examples that we exposed, like normal maps, reflections, box corrections, shadows, render sizes, capped frames, anti-aliasing, and everything. So we can adjust everything. And what we did a fine-grained granular quality settings. So first, how quality settings works is if a quality settings exists for a specific device, then we use that quality setting. If it doesn't exist for a specific device, since this in Android world is quite possible because there's a wide range of devices, and you can manufacturers reuse hardware but just on a different model. So after we try to find a specific setting for a specific device, we try to find its settings for the GPU, since this is the next big indicator what this device would work like. And if we don't find that, then after it, we just revert to an API. So if it uses a Metal API, it's probably a pretty strong device, so we can have a higher setting than for an OpenGL ES2. So with these fine-grained settings, we actually ensure ourselves that if we forgot a device or we didn't know about a device, that it will run, well, more or less optimally until we get the time to get our hands on it and actually make valid settings for it. So like make almost all the settings exposed, do settings for them, do tests on the device. And this is kind of would require a lot of time if you need to rebuild your application every time you change some settings. So we have dynamic settings, and we wrote a tool for it. This is a screenshot from the tool, and also this is a GIF from the action. So I don't know if you can see it, well, probably not, but down here you have this tool. You can change these features in real time, and it uploads to the device, and it's changed dynamically on the device. So you can actually get results pretty fast. And we have an FPS graph that we just measure, like, okay, these settings dropped our frame by our FPS by this time, or by this much, or this setting dropped by that much, and then we make combinations. So we decided not to group them in tiers, but we decided to make all the settings exposed because not all devices react the same way for the same settings. So maybe some have problem with normal maps, some have problems with anti-aliasing, so we find that this is the best way to do it. So yeah, write your own tool if you have the time, of course. It always pays off. So we actually get pretty close to the end of our talk. We just wanted to make a short recap about what we talked about. We want to say that writing custom PBR shaders really pays off. In our case, at least, it paid off, and we recommend you do the same. Both for artist control, and you get way more out in performance side than using a solution that's used widespread. Next thing, use GPU profilers. Use them to the fullest, like we used to get actual shader instructions and reduce the complexity of the shader. Use your shader variants wisely. If we had the choice, we probably wouldn't implement a system that replaces Unity's system because it's way easier just to use Unity's. So try to use them wisely and try to avoid writing custom solutions, but you absolutely have to. We just show you a means how to, so you can use something like that or make up your own solution. We can't stress this enough, but MSAA, in our case, is free. At least we didn't find a case where it's not. We're sure it happens sometimes, but always check. So it's better to use upscaling. It's better to render in 720p than upscale it to 1080. With anti-aliasing, you get way more performance and less heating, but it mostly looks the same. Like if you don't notice the switch, you will never notice the difference. And of course, pull and preload objects to get to the silky-smooth FPS. So yeah, that's it. I hope that at least somebody took something, at least somebody saw something new, that we didn't repeat some obvious stuff. And I hope to see maybe your AAA quality game sometime soon in another Unite or somewhere in the future. So see you then. Now we have some time for questions. Actually, before we go to questions, so our company, Nordeus, also had another talk about VFX in our game. So we mostly focused on PBR and general optimizations. But if you want to see how VFX is done, you can visit our colleague's talk, Nicola's talk, on, I'm guessing it's going to be uploaded somewhere. And I really suggest that you look that up because it's a quite interesting talk. Also, on this slide, we just wanted to leave the link to our GitHub when you can download the Overdraw tool. We just hacked it up in a few minutes, but it should be working, and it should help you a lot with determining how much Overdraw you have. So yeah, we are now open for questions.
Yeah. Thank you for listening.
Hey guys, great talk. Thank you so much. I have one question. You mentioned using GPU profilers, and you mentioned the Adreno profiler. Did you also try using the shader profiler in Xcode? And how does that compare to the one for Android?
Yeah, it actually works really well. The only thing that you need to be aware of is that you need to switch your profiling platform or scheme, or however it's called in Xcode, to metal before you actually profile metal, or it won't work. And we found it really well, but the Adreno profiler has faster iteration times for us. And we kind of found that if we fix something in Adreno profiler, it will also be fixed on iOS devices as well. So we first go with Adreno profiler. And if we still have problems on iOS devices, then we get to Xcode profiler.
Thanks.
I just wanted to say one more thing. Mali profiler is now natively supported in Unity 5.6, so you can use that as well. It's also pretty cool. Mali graphics debugger, actually.
We can make also honorable mention to the new Snapdragon profiler that is, since the Adreno profiler is not supported on newer devices, but the Snapdragon, we find the Adreno profiler to be better at this point, but we are hoping the Snapdragon profiler will get to the same level, at least soon in the future.
Hey, did you have the chance to play with RenderDog? Because they have a really neat feature that's about calculating the cost of every draw call in microseconds. That's normally simulated, like in OpenGL I think. I don't think it's accurate, but still the relative timings are pretty good.
Yeah, you said render doc, right?
Render doc, right.
Yeah. We couldn't get it to work on mobiles. I don't know if it can work on mobiles.
Yes.
Oh, really? We need to talk.
Well, I think you can simulate
Okay.
the rendering costs.
We need to talk afterwards. But yeah, we used it for some PC stuff. And yeah, it's pretty cool because, as you say, it can actually do those timings, and it can also tell you what parts of the shader changed, what pixel and how, which is pretty cool for debugging when you have some black spots somewhere.
And I think Intel offers another tool for that. I forgot the name, but they also do timings, and they render the same frame like 1,000 times, and then they make averages.
Yeah.
And I think that works also for Android.
Yeah, actually, Adreno Profiler also has timings, but they're very well hidden. There's a button just above the draw calls where you can select to show clocks.
Yeah. Hi again. Thank you for this talk. I want to ask you about shadows. You have just plane and units on it. Why not use projective shadows without any depth calculations? Just project unit at the plane, and you can get smooth shadows without any cost, without PCF. And also, why you not modify light maps baked by Unity? Why you use custom solution? Because, for example, you can bake shadows, or bake light maps, then modify it, and then use it in game.
Okay, so first question I didn't really understand. So you think like having casting directly minion geometry to a plane?
You can use a minion like something that you can project on the plane. So it's just one matrix. And
yeah. We actually had that solution implemented once. And also tried stencil shadows because they're slightly less expensive than the render texture and this solution that we're using now. The problem is that we get really hard edges, and then artists complain how the shadows are hard and not really that nicely looking. So, and also we would have a bit of a problem to combining them with the light maps, since you need the information from the light map, and if it's a separate draw call where you render the shadows, cast them to the plane, you cannot really do that.
You can actually draw a plane in some render texture with shadows, and then look up there and combine with light map. Also, you can use trilinear filtering on that texture to get smoother shadows. Because, for example, I have project which used that technology, and same setup, plane and units, and it works very well.
Yeah, we could have done that, but the thing is that we wanted also self-shadowing. So I don't know if you noticed, minions do have self-shadowing.
Yeah, it's the case, yeah.
Yeah, but that's not really noticeable, and they're casting shadows on the foliage all around and everything. And also, we are having some like close-ups to the characters somewhere in other parts of our game. So we just want to use the same shader where you can have the shadowing from the head and stuff. And your next question is asking whether we are...
Why you not modify light maps baked by Unity and use your own solution? Because it's possible.
Yeah, it's possible, and we did that actually. So. Earlier, we wanted to, when we baked the Unity light maps, we added some small tweaks, so like tweaking the color and stuff, just for the artist to be more satisfied and add more variation to the scene. The problem nowadays is like the light mapper is changing really fast, and baking it in Unity, I mean, it's not a sustainable solution. So this kind of gives us the best quality, and the artists are more happy.
Yeah, so you're just not happy with the Unity light mapper tool, not the situation you have?
Well, at the moment, we feel that we are better this way.
We have high hopes for progressive light mapper, but it still has some bugs in our case, so we cannot use it yet.
And what kind of bugs? Light leakage or shadow leakage? Or
all of that plus everything is black if we try a 4K light map.
Thank you.
No problem.
Hi, you mentioned that on some devices you don't do the upscaling, so I wanted to ask, do you do upscaling on like iPad and high-resolution Android tablets?
So we don't do upscaling on iPad Pro because the screen is so big you would very easily notice it, and it's also powerful enough. And the newer iPads, we also do very little upscaling because of big screens, but older iPads like iPad 2, iPad 3, iPad 4, we do upscaling on all of them.
So you just specifically say for which devices you do which kind of upscaling?
Yes, yes. We try to go with GPU first, just so we have less work to do. But if some devices have very different screens but the same GPUs, we specify per device.
Okay, thanks.
Hi, thank you for the talk. Have you considered matcap reflections instead of cube map reflections for this game? Because the camera is only from one perspective. Is this something you considered?
I didn't hear what you said. Instead of cube maps?
Matcap reflections, like 2D reflections based on camera.
Do you mean planar reflections? Planar reflections.
Yeah, matcap, basically what also ZBrush uses. It's just a texture, a 2D texture of a circle mapped on the direction of the normal from a camera perspective.
So I think it's something like paraboloid reflections. We did, I think, if that's what you're talking about, so we did use that in our other game, but it was just simpler to implement this system. And also, we need glossy reflections. And they're natively supported by Unity, so just it's easier to implement it because we already have that and Unity generates it for you. So you just take it and use it. And it gives satisfactory results.
Okay.
Like the performance is fine.
Yeah, and one more thing, we didn't show the entire battle flow. When you enter the battle at first, there's some intro camera where it kind of has different angles. So we also need something like that as well.
Okay, good. Thank you.
Yeah. Oh. Cool.
You mentioned modifying PBRs, a PBR shader. Did you did your own custom PBR shader from scratch, or do you use in some parts of Unity system, and which parts are left and which parts are changed?
Yeah, well, when we were writing our shader, we wrote we worked closely with the artists and asked them what they needed. That's the first thing. So we wrote it from scratch. We didn't take. Since I was writing it, I was looking at the Unity shader, how it works, just kind of for the research thing. But we were mostly writing it from the scratch. When I said using Unity's parts, we meant like using luminance or I don't know which other functions. So like this single functions from the Srdja include. So not actually using the PBR parts of their shaders. So just these single functions. I don't know if that answers your question.
Yeah, thanks.
Yeah, I just wanted to expand a little bit. We didn't want to go with Unity's lighting model because it has 3 tiers of scaling, and we wanted our scaling in the shade to be more granular. That's also one reason why we didn't want to use Unity lighting functions. Yeah, and this is, I think, the 4th shader we wrote from scratch, so we have good practice. Okay, I guess that's it. We'll be right outside if you want to catch us, and thank you very much for listening to us for an hour.